Okay. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. So, how are you doing? Alhamdulillah. Okay, you all look happy. That's good. Inshallah today we'll be even happier. So we're done with the math part, the pure math part. Now we're going to be having the application part. So we're done with the mathematics part. Now we're going to apply this mathematics. Okay, so it's not, we're still going to see a lot of equations. But at least you're going to be seeing really we're going to do really the robotics from now. Always keep in mind, okay, just as a test for yourself. I cannot test, okay, your experience, but imagine if we would have started the course from here. Always keep that question in your mind. And you did not know about the stuff that was done, How important is the previous, topic? Always keep that in mind, okay? It will appear all over the place. We're going to be using this language, but we could have been, you're going to be seeing today that we could have just introduced matrices and just, start calculating, okay? And now I hope you're going to be appreciating, the stuff that we did by looking at this stuff. So let's start with an introduction of topic number 2, robotics. So yay, pictures of robots. Okay, so I did not lie when I told you this is a robotics course. So most of the robotic systems that you see out there, okay, they usually contain rigid bodies and joints. That's it. Okay, you just have one rigid body and one joint, one rigid body and one joint, and so on and so forth. So the goal of this topic number 2, and the beginning of topic number 3 is actually we want to model rigid bodies and learn how to interconnect them together through the joints. Okay, the joints we're going to be keeping to next topic. So this topic number 2 is only about rigid bodies. What is a rigid body? How do we model it mathematically? What kind of mathematical tools do we need so that we're able to write equations that describe how this robot moves, and so on and so forth? Okay, both kinematically and dynamically. This approach we're going to be using is called the Lie group approach for rigid body kinematics and dynamics. And in this, approach, the most fundamental, object is SE3. So SE3 is known as the special Euclidean group, and this will serve for us the configuration space of a rigid body. Okay. So whenever we want to describe, if I give you one rigid body, for example, imagine this phone, and I tell you, okay, this is the one configuration of it, this is another configuration, this is another configuration, and so on. What is the mathematical object that will incorporate all of these configurations, which is what we call the configuration space? And this will be what's known as the group of proper isometries of Euclidean spaces, which is known as the special Euclidean group. Of course, for this is just still a lot of terminology, but this is hopefully the goal that you should be understanding at the end of the lecture. So this is a very nice book called The Geometric Fundamentals of Robotics. And it's stated inside of it, this group, which is the SE3, is perhaps the most important one for robotics. Okay, so if you really understand, it's not just about rigid bodies, it actually goes beyond that. It appears a lot if you want to do advanced state estimation, if you want to do advanced Kalman filtering, if you want to do advanced system identification or parameter application, it's nonstop. Even if you want to do advanced learning algorithms, SE3 and the geometric way of looking at of systems is very, very important. The way we're going to be starting is the following. I'll not jump immediately to matrices. Okay, now you should expect that we're going to be starting from a coordinate-free way of describing things, trying to just think about everything without numbers, and then at some point we're going to be introducing the numbers, and then we're going to be starting work in the end with matrices. Everything we do from now on will be just matrices and matrix multiplication. And because of that, this is the most important point that you have to keep in mind. It's very important to always know the mathematical nature of the matrix you're working with. In the end, we're going to be doing, matrix multiplication. I promise we're not going to do any more complicated, at least in this topic, we're not going to do anything more complicated than that. But afterwards, you always need to ask your question. What is the nature of the matrix I'm working with at the moment? Okay? And we're going to be seeing some of the examples today, inshallah, and throughout this topic. Sorry?
Coordinate free. What do you mean here by coordinate free?
What I'm going to do now. Okay. Okay. So the coordinate-free way, we're going to be introducing 3 abstract concepts, 3 concepts. Okay. So no numbers. The first one is an n-dimensional Euclidean space. The second one is what is a rigid body and what is a coordinate frame. So 3 things. Okay. First, with the Euclidean space, or as an example, it's just like, we can also call it an ambient space, but I'll just choose the Euclidean space. It's n-dimensional because it's simply an abstraction of the physical space we're living in. So this is Euclidean three-dimensional space, this room, okay? Mathematically, it's a manifold. Okay? Mathematically, we're going to be saying it directly, it's a manifold. What is the set? It's the set of all of the points in here. So you see here, all of the green dots there, okay, they are physical points in this Euclidean space. Okay? So this is a point, this is a point, this is a point, and this is a point, right? And associated to this capital E, this capital epsilon, is a vector space. We're going to be calling it epsilon star down. Don't think of this star as related to the dual. No, that's why I wrote it down. You know, it's just the name of the space is E star. That's it. So if you look at any element of E, you're going to find points. If you look at any element of E star, you're going to find free vectors. Free vectors is something we already have, and we always think about it. It's actually directions. Okay? If I tell you how am I moving right now, what will you say? Like this, right? You see, everyone from you, he had a different arrow, right? Placed at a different place, and they all mean the same thing. They all describing my motion. You did not need to use any numbers, right? You did not tell me you're moving in 0, 0, 1 or 1, 0, 0 or anything, right? It's all just abstractly what it means. So that's exactly what we mean here by free vectors. Okay? We also need something else. So this space like that, okay, with these abstract points and these abstract vectors, they give us what we need, but we need an extra structure to be able to describe. If I give you 2 points, you need to always associate to me some positive number that defines the distance between them. Just the distance itself, okay? So for example, if I tell you these 2 points, they have a distance of 0, what does that mean? They're on top of each other, right? They're the same point, essentially, right? And if they have, 1 unit, they're like this, 2 units, they are like that, and so on and so forth. You can always associate numbers, positive numbers. There's no such thing as negative distance, right? It's only positive distance between the 2 points. You cannot talk about distance of vectors. You see, that's why epsilon here, it's not epsilon star. So now you see, okay, we're going to have a definition between vectors, free vectors, the abstract free vectors, which you see here as arrows, and the abstract points, which you see them as the green dots there. Clear? No numbers, everything is just abstract concepts. So that's what an Euclidean space is. What a rigid body is simply mathematically 2 pieces of information. It's a set, which is a subset of the Euclidean space, and it contains all of the points that have matter inside of it. For example, here, what's inside of here? Nothing, right? There is no rigid, there are no points. Of course, there is air, but forget about air. And imagine that this is just nothing there. And now, what is here? Points. An infinite number of points that make up this object. Okay? So each one of this point on this object, okay, in the end, they make up the set B. And we also need to equip it with something else so that we can differentiate between this object and that object. We also need to associate to it a mass density function. Okay? So it's a function from B to R plus, and simply rho of P is a positive number that defines the density of the body at that point. Okay? Because, for example, if you look at this body, this point has different material from here, right? So if I calculate this point, the density here, I'll find it different from here, and so on and so forth. Okay, and there is no such thing as negative density. It's always positive density. Make sense? Very simple, abstract stuff. Nothing, complicated. How do we talk about numbers? Yes. You'll see that later on, which is when we start talking about the dynamics. I'll give you some stuff to read because we'll not have time to describe it, but you'll see how important it is just to start from the density itself. Okay, that will appear later. The coordinate frame is 4 pieces of information: 1.0 and 3 free vectors. No, not bases. Okay, there are 3 options. Okay, 3 directions that you choose. And you say, first of all, they are linearly independent, and they are orthonormal free vectors from each other, which in the end, they serve as a basis for what? For the vector space E star. So that's why you have to choose 3, because of course this is, I'm having the picture here, always n equal to 3, right? You can easily talk about 2-dimensional Euclidean space. Nothing will change. Okay, but we'll just keep on from now on from 3 dimensions. Okay? So this is a choice of basis, because what is a coordinate frame? It's this. So the white point, imagine, of course, this is just a point now in the space. It's not that big and doesn't have any volume. It's just a point. And these are the 3 vectors that you choose. They could be like this, like that, and so on. First of all, I'm going to be using these tools a lot, and that's attributed to Tarek. Okay, so Tarek, he produced them last semester. Okay, so yes. It can be anywhere. Okay, and this is, I think, the next slide. Yeah. So before that, okay. So what do we use these coordinate frames to do? We use them for 2 things, and you usually mix both. But now I hope you're going to see that they're actually use them in 2 different ways completely. We can use the coordinate frame to represent any point by 3 numbers. And I can also associate to any free vector 3 numbers. Right? Can I repeat? Okay. So if I tell you this is the frame, and it's exactly here, and I tell you this is a point now, can you give me some number that corresponds to that point? It's what? Coordinates. Yeah, exactly. That's why it's called the coordinate frame. So if you tell me the P, so if this is the point P, exactly what I have here, what would be its coordinates in this frame? It's like I did not move in the Y, I did not move in the Z, I only moved in the red arrow, which is the X. And if this is 1 unit of length, this is maybe like 2 units of length. So in the end, it's like 2, 0, 0. If you tell me 2, 0, 0, I know exactly which point you're talking about. But if you remove the frame, I cannot talk about numbers. So that's the abstract point, and this is so this is the R3, and this is the P itself. Abstractly, it makes sense. With numbers, it depends on the choice of the basis. There was some question. Yes, Fahd.
The origin of the place where we put our coordinates.
That's exactly, yes. You choose it. It's one of the points in here, and I have to say, it's this point. It's where numerically, it's the physical point that corresponds to the 0, 0, 0 coordinates. Okay? So if you have a number of 0, 0, 0, you need to know where you are. Right? It's this point.
Can we say the point which all the coordinates or all the dimensions start from?
That's exactly the 0, 0, 0. Yeah, exactly. Yeah. It is the 0, 0, 0 point. It's the physical point that has 0, 0, 0 as numbers. Okay? And it's a choice. Okay? And you're going to see exactly why it's a choice. Once we talk about rigid bodies, it's a choice. For example, if this is my rigid body, so there was a question here, why don't we put it on the body? Of course, you can put it on the body. You can put it anywhere. Here, for example, I put 1 frame here in the corner of the room, and I can also put another frame here. Where do you put the frame? For example, imagine if this body is this phone, for example, and this phone is like a very small aircraft. Where do you put the frame? In the middle, right? What is the middle? Here, 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 here. Does it matter? It might. Yes, of course, it does matter. Depending on which tools you have. In the ways we're going to be working with, it doesn't matter where you put the frame. It doesn't matter where you put the frame, because we're going to be working in a way that's coordinate free. So it matches the coordinate free. You're used to the way of working that's based on the coordinates. And now this is a very big statement. I have to prove it to you, which will take us many weeks. But keep that in mind. Okay. So the numbers that we associated to the coordinate free is simply anything without numbers. It's coordinate free. It's an abstract. It's a concept that's abstract, makes sense. For example, when I said the manifold, doesn't make sense to you or not? Now, yeah, it's the points. If I told you the vector, the direction, it's a vector space, right? If I tell you positive direction and negative direction, it makes sense. If I tell you this direction plus this direction, you tell me, yes, it's that direction. If I tell you move north and then east, you tell me, yeah, of course, it's like moving that way. We can talk about it without any numbers, right? That's the abstract concept. All of this coordinate free, yeah. because we're not using any numbers to describe. Okay. The numbers come only with the bases, or with the coordinate frames. And the coordinate frames, I used it here to associate numbers to points, but I can also associate directions, okay, to the numbers. For example, that's a different way of looking at it, because if I tell you what is this direction now, give me 3 numbers corresponding to it. 1, 0, 0. It's a direction, right? It's a unit vector. You know what unit vectors are? Just directions. What about this direction? You see, you all talk about numbers, right? What about this direction now? -1, 0, 0. It's the same direction, but depends on your choice, depending on how you're looking at it. For example, could you make your hand like this? This is your x-axis. Could you make your hand like that? No, could you make your hand like this? This is your x-axis, okay? We'll keep them up, keep them up. Am I moving in positive x with respect to you? Am I moving positive x with respect to you? No. So you see, the numbers, positive, negative, 0, they all depend on your choice of the base.
Talk about because we are now talking about SE3.
Oh, no. It's a very big concept now. We're something very, very basic.
When we are choosing the XYZ, we have to choose based on the right hand rule. So at the moment,
Not yet. Not yet. We're not talking about it yet. We'll come to that later. Yeah? The 3 vectors, the V is the direction. This direction, that direction, this direction.
Something from the origin.
Yeah? What origin? That you chose. That's something else. What you said exactly right now is one of the biggest misconceptions that you have to start with, which is we've all seen the fact that any point can be called 0p, and 0p is a vector. And then you can start talking about numbers. This should make sense to some of you. You know, the 0p vector that starts from the origin to the point, and then you're talking about a vector. This concept is exactly mixing 2 things. The numbers we associated here to the p, which is a point on the manifold, are actually a chart. They are actually they are Cartesian chart for the manifold. While the 3 vectors we chose here, which is the same, the numbers that we chose here and the bases they correspond to are a basis for a vector space, and they're not the same thing. And this is a very big statement. I'll not be able to, we don't have time to go through it. But if I change coordinates from Cartesian to polar coordinates, they will not have the same shape, right? So this will be, for example, R and like theta and Z, for example, like cylindrical coordinates. But this will be something else completely. There'll be the direction of R and the direction of theta and the direction of cylindrical, and things will get very, very messy. And there's no time, unfortunately, to go to that. Okay, this was a very good exercise we could have done, but okay, it will cost us a couple of robotic stuff. So we have to compromise on that.
is it always going to be in terms of unit vectors, or we can have actually bigger numbers?
You can have you can have bigger numbers. That's a good question. So I think let me rephrase the question. So is the space of free vectors, does it only contain unit vectors? I think that's a real question. It can contain other stuff, right? Because I can tell you I'm moving in this direction, okay, and I'm moving in the same direction but twice as fast, right? I'm moving in the opposite direction, half as fast or twice as fast. I can talk about bigger vectors and smaller vectors. So they make sense. Free vectors make sense without talking about points, and even without talking about distance to points. Okay, so we're not talking about this.
Let's say 2, 0, 0. I shouldn't jump to the conclusion that this is a distance to that point. It could be the velocity we are talking about.
Exactly, absolutely, yes. So let's move on. This is usually the setting that we start with. We start with a setting where you have some observer that's looking at things. For example, your camera, your sensor, you yourself, you're looking at the stuff. You're just an observer. You don't have any matter. And then you have another rigid body which corresponds to your drone or to your robot that's moving on. And you have the environment, which is another rigid body that this drone will go there and it will start interacting with it and so on and so forth. So What we want to do right now is that we want to be able to describe the pose of a rigid body. What do we mean by the pose of a rigid body? It's the combined orientation and displacement of that rigid body. And we can do that even by talking about the Euclidean space itself. And you see here something that we're going to be replicating the Euclidean spaces. Okay, this is just, a mathematical part. We could have talked in a different way, but this is just, it's an easy way of, it's a choice, to be honest. Okay, but imagine that every, object that you're thinking about, like, it has its own version of this Euclidean space. And simply the relative pose between two Euclidean spaces, epsilon I and epsilon j, will be denoted by a map that takes you from I and brings you to j. A map that takes you from I and brings you to j. It makes both of them the same, okay? And the set of all of the relative poses between the two objects, we'll be calling it SE, I with respect to j of n. In 3 dimensions, n will be 3. Okay, and it depends on the I and the j. What is the I and the j here? The two different objects you're talking about. For example, I can talk about the pose of this object with respect to that object. And I can talk about the pose of this object with respect to that object, right? And this object with respect to someone who's looking, at the sitting at the chair and is looking at things and so on and so forth. So this is the relative pose. Everything will be the same. If it's moving, you have a rate of change. And you need to talk about differentiability. And this is why we have the manifold structure. Think about it this way. So this is only just the set at the moment. What is the set we're talking about? It's just abstract relative poses. Yes?
Both modes are selected or independent to each other?
Everything is independent. Each one of these bodies is independent from each other. The robot is different from the sensor or the observer, and the observer is different from that environment, and so on and so forth. Okay? And then we can now talk about numbers if we associate to each one of these individual Euclidean spaces a basis. Okay. So this is usually what we do. You always have to choose a basis, or you have to choose a coordinate frame. You say, for example, this body has this coordinate frame and it's fixed with it. If the body does like this, the frame changes with it. And then I have another body that has another frame, and they're both changing, they're both moving with it. And I can also have a frame that lives with itself. It's just looking at stuff. I'm representing everything with respect to that frame. Okay, or not. Okay? It's a choice. You can always represent. I can always talk about the drone with this. So, for example, if this is the drone, I can talk about the drone with respect to the environment, or the environment with respect to the drone, or the environment with respect to the observer, or the observer with respect to the drone, and so on and so forth. Every pair, I can always talk about the relative pose of them. How do we go to numbers? We simply, because we chose a basis for epsilon I, and we chose a coordinate chart, which is the frame. So any point here or any free vector here, I can give it some Rn, and any vector here or any point here or any vector associated to it in the epsilon j star, I can give some numbers here. So in the end, we're looking at a map between Rn to Rn. Okay? So if I want to describe how one frame looks with respect to another frame, I just need to have a map that goes from Rn to Rn. Simple as this. In this case, Rn is it's a vector, of course. What is n? And usually in 3 dimensions. You're talking about robotics in 3 dimensions. Okay, if you have in 2 dimensions, things you can always simplify stuff. Okay? Now we're going to be linking that what I just discussed to stuff that we discussed before. When I say a map from Rn to Rn, what comes to your mind? Endomorphisms, or linear maps from Rn to Rm. Okay. So you remember this picture? We had the linear maps from Rn to Rm. Inside of them, we had the case where n and m are the same, which are the endomorphisms, and inside of them we had the automorphisms, and we said that it has a group structure that we can call it the general linear group. Okay. And inside of it, we said we can have matrix Lie groups from last time. We can always have a subset of it. Again, we did not discuss much about it, but he said, okay, in principle, any subset of it that's closed, it can work as, as a matrix Lie group. We said that Rn has a manifold structure, okay? And this has a manifold structure coming from it, and this has a manifold structure coming from it, and so on and so forth. The question is, this map we're talking about, where should it live? First of all, can it live in the N to M matrices? No, it does not live there. It has to be inside of an endomorphism. You remember what were endomorphisms? How did it, if you take any point here, what does it look like? What kind of an N by N matrix, exactly. An N by N matrix. This is exactly the idea of a map from Rn to Rn. You remember when we said I have a vector space and a vector space? What would be the map that takes me from, a linear map that takes me from Rn to Rn? Just an N by N matrix. You've always done that, right? You multiply an N by N matrix with an N by 1 vector. What do you get? N by 1 vector. So we mapped from N by Rn to Rn. The question is, what should we allow all maps on Rn to act as our description of rigid bodies? In other words, if this body moves from here to here, okay?
To have a bijective inverse?
First of all, that's an excellent question. Yes. Do we need to have bijection? Yes, of course, you need to have, because I can take the body from here to here and I can bring it back. So in the end, I cannot have any map. I must have invertible maps. So actually, this space is already out of the game. I cannot have any endomorphism. I need to have an element from a general linear group. It has to have determinant not equal to 0. It has to be determinant not equal to 0. That's good. So that's a good starting point. Do we need any more constraints? Can you think of something?
Yeah, it also needs diffeomorphism smoothing.
It needs to be smooth. That's right. And that's why we said that this has a manifold structure. We cannot have, this is the configuration now, and it's here. Do you see that in real life? Have you ever walked next to a robot and then it disappeared and it appeared somewhere else? So you need to have differentiability.
Also move like this, discontinuous.
Discontinuous?
Example,
It disappeared from one point to another point?
trajectory like this.
But that's if this discontinuous means at the same instant in time, it was in two places. This is what discontinuous means.
Here, continuous, but not differentiable.
Very good. Exactly. It's not differentiable. Do you need some constraints on the differentiability? Yes, of course. You need to talk about Newton's second law. You need to talk about velocity and acceleration. So we need to differentiate once and twice, okay, and so on and so forth. We're not going to be thinking about differentiability. Remember what we said? We're going to be assuming everything is smooth. Like just for simplicity's sake, everything is smooth here. So the manifold structure is C infinity. We have just everything is smoothly, okay, and continuously differentiable. So that's okay. So that's the differentiability requirement and the invertibility requirement on the map. What else? Can someone think of something? I'll tell you immediately what the answer is. The answer is that if you really want to know what type of maps we should allow, they should simply preserve the distances between points. A rigid body is simply, if I tell you this point and that point, before moving it and after moving it, they should be same distance. If they were not, what does that mean? It's not a rigid body. Right? It's not a rigid body. It's what you call a flexible body or an elastic body. Right? So this is not what we're talking about. We're talking about rigid bodies. If you do that for any 2 points, actually not for any 2 points, it's like for every pair of points. So this one with all of the other points and this one with all of the other points. This is exactly how mathematically we can represent it. That the distance between any 2 Rn's before the isomorphism, before the map and after the map, see, because I have here the vector after I moved it. So this is the vector v after I moved it. And this is the vector v before I moved. And this is the vector w after I moved it. And this is the vector w before I moved. You calculate here what is this called? The norm. How is the norm calculated? The square root of the vector transposed with itself, right? You're going to have that in the homework and you're going to play with it a lot, inshallah. And also there will be some MATLAB stuff so that you can see this, okay, in action, okay? But take my word for it for now, that the maps that will correspond to rigid body motions must preserve the distance between the points, okay? Or between vectors in the end. And these maps, they actually have a very special name. They are called isometries. Okay, so such a map is called an isometry on Rn.
Here, both here are n, but يعني, sometimes it is first norm or second norm, but here I think it is somehow confusing.
Yeah, okay, I see your point. The norm itself, what norm are we using? There's something in this is an aside, discussion, but it's very interesting on its own. Norms in finite dimensions are all equivalent. So the one norm and the two norm and the three norm, all of them are the same. They are all isomorphic to each other. There is no extra information. In infinite dimension, that's not the case. If you have an infinite dimensional vector space, you can still talk about norms, and it makes a difference whether you have the one norm or the two norm and so on and so forth. This is something very important for people working in discretization. People working, trying to build code simulations, like COMSOL or ANSYS and all of these simulations. This is the number, yeah, exactly. The number will be different. But in the end, if you use here the two norm and the two norm, or the one norm and the one norm, it's all the same. That's why they are isomorphic. It's not that they can be equal in the two norm and not equal in any other norm. Exactly. Doesn't know what is the easiest one? The two norm. It's just, it's usually the most, easiest one. It depends on the application, of course, but to do math, usually it's the easiest one. Isometries on Rn, you can show mathematically. You just, we need to spend some time also on that. But if you want, you can dig deeper with that. They correspond to three types of motion, only three types of them: translation, rotation, and reflection. Okay. Can we show that mathematically? Yes, you can show that mathematically. And this is a big jump, okay? But again, I don't want to spend time in this, in this stuff, because it will eat from the robotic stuff. So I was in doubt actually I did not put it last year in the course, and I was also doubt to put it in this year or not, and I decided not to go for it in the end. You should take my word on it that isometries, okay, they always can be written as some n by n matrix multiplied by v plus some r offset. What did we call this map before? Does anyone remember? An affine map. Is it linear? It's not linear. It's an affine map. Okay. So there's something here that you remember when we said it has to be invertible, right? It has to be general linear, but it seems that if we only restrict ourselves to the general linear group, we can only get the rotation and the reflection, but you cannot represent the translation. And this is why the translation actually is an extra piece of information if you could have it. Okay? And this is how you can get this equation. The M itself, it cannot be any n by n matrix. It must be belonging to what's known as the orthogonal group. You worked with this in the assignment. Okay? How is it defined? It's simply the set of all n by n matrices. When you multiply it by its transpose, you get the identity. Okay. So this is a set, and the M here. So remember what I told you, that these isometries, they can either be translation, reflection, or rotation. The translation is simply this, this psi. Right? If I have, let's assume M is identity. Okay, so you can imagine that I only take all of the points on the vector and I add to it some numbers. All of the points have the same numbers, like this or like this or like that. So I'm just doing what? Translation. If I don't have any translation and I just multiply it by M, I can have only rotation. Okay, or reflection. Of course, reflection is not what? Reflection is not what? Reflection and rotation are different things. But can you have a robot and you can tell it to you can command it to move in the front, and then suddenly it reflects? Physically not possible. No, you can go back and forth. If you can reflect, you can go back and forth. You know where you see reflections? Where do you see reflections first? In the mirror. You look in the front of the mirror and you see yourself. You move, you're still the same. You look in the front of the mirror. So you can go back and forth. It's still a bijection. Makes sense. If you can translation, you can go forward and backward. Rotation, I can rotate like this and I can go backward. Reflection, I can reflect and I can reflect back. No. It's all possible. It's not physical. That's the word that you're thinking about. It's not physical. We never see it. So what we need to do right now is simply, we need to exclude these reflections. We need to keep translations and rotations and remove the reflections. You can actually see it mathematically. Just by saying that this matrix must have, when you multiply it by its transpose, must have an identity, it already implies the determinant of the M should either be +1 or -1. Did I put that in the homework or not? I did not. Or yes or no? I did. Okay. I don't think so. Let's do it a very quick check. What is the determinant of the identity? 1. What is the determinant of two matrices multiplied by each other? Multiplied by the determinant of the second. So if I have the determinant of M and M transpose equal to 1. First of all, the determinant of M and the determinant of M transpose, are they the same? Yes, they are the same. Yes, they are always the same. The determinant of A or the determinant of A transpose is the same number. So right now I have determinant of M squared equal to 1. So what could be the determinant of 1? Determinant of M? 1 or -1. That's a quick proof of this. If you have an M that has the determinant of 1, it simply corresponds only to rotations. If you have the determinant of M equal to 1, you actually have the reflection. Okay? You're going to have a MATLAB code and some nice mathematics assignment to actually see this in action and play around with it so that you really grasp, this idea. So right now we have, this is the set that we said, okay, they correspond to what we want to describe the M's. And this is the set that we need to restrict inside of the ON, the orthogonal group. We need to restrict, we need to exclude the reflections and look only at the rotations. And that's why we're going to be only looking at the elements in ON that have determinant equal to 1. And this has a special name. It's called the special orthogonal group. Any element from the SON will correspond to what you know as, or probably have heard about before, as a rotation matrix. It's a matrix. If I multiply it by something, what it will do? It will rotate it. Okay? In 3 dimensions. Okay? So rotation in 3 dimensions is something like this. Like this. Like this. Like that. This is rotations. This is rotations. All of this. Okay? In the end, the origin will be the same. It will not be translating. So now we have the mathematics for rotations. What about the mathematics for translations? Simply just add this Rn. Okay? So in the end, now we have that the isometries. So now let's go back a little bit. So if I have any two Euclidean spaces, I gave each one of them coordinates. So I give this one coordinates, I give that one coordinates, and I have an abstract notion of relative pose between the two, between two with respect to 1 or 1 with respect to 2. And we saw that they are equivalent mathematically to this n by n matrix. Okay, so sorry, not an n by n matrix, to be precise. It's a map from Rn to Rn that's in the end is equivalent to this notion of an n by n matrix in addition to an n by 1 vector that corresponds to the translation. So this is what corresponds to the translation, and this corresponds to the rotation part. Because we're talking about two rigid bodies or two Euclidean spaces, the Ri with respect to J corresponds to the relative orientation of frame I with respect to frame J, and the psi I with respect to J represents the relative displacement of the origin of frame I with respect to frame J. Okay, so when I tell you I have this frame and that frame, and I have an Ri from I to J and a psi from I to J, you know exactly what we're talking about physically, right? It's the relative displacement between the 2 points, okay? But of course expressed in one of the frames, which is always the one on the top. Always the one on the top is where we express stuff, is where we're looking at stuff. And I have the relative orientation between the two. Any questions? Clear? So now this is going from the abstract notion of, just starting with a set, just an empty space of a manifold that has all of the points and all the directions. Now how we can go to numbers and how can we go in the end to matrices. Okay? The product of SON with Rn, it simply has another special name, which is called the special Euclidean group. And we usually take these two together and call them SEN. Okay. What I just wrote here, okay, you need to be very careful because you need to ask me what. What's the natural question you should ask here? When I say this times and this is equal to. No, the order doesn't matter. What type of operation is this? That's a very good question. Not multiplication. What was it called? What was this called? The Cartesian product, exactly. So this is as a set, and this as a set. I just, if I give you a bracket, one of them has R, one of them has psi, where R lives in SON, and the psi lives in Rn. This is exactly, these two together are called an element in SEN. That's exactly what the times is. We started in the first lecture, we talked about it. The Cartesian product of two sets. It's an ordered pair. Yeah, exactly. The order doesn't matter. Oh, sorry. What the order doesn't matter, I mean, is that we could have defined Rn first and the SON first. Nothing would have changed. And it's isomorphic to each other. Whether you say AB or BA, doesn't matter. The order doesn't matter. If I say Ahmed and then Muhammad entered the room.
B بس يعني A Cartesian product B not equal B Cartesian product.
That's right. Absolutely. Yes. Absolutely. You're right. Yeah. Exactly. Yes.
So on the transformation frames, right?
Between frames, yeah. The transformation between frames. The translation part. Because we said that the psi, sorry? The psi here. That's right. No, so you see here this? We're going to be taking this whole space and we're going to be calling it, we're going to give it one number. So any bracket, any pair of R and psi, we're going to be calling it SEN. It lives in SEN as a pair. Clear? So this is only as a set. So the natural question is, what kind of structure could we give it? From the name, you should already see that. We can make it into a group. Can we make it into a vector space? It's a matrix, right? And it's R3. First thing you think about, let's add matrices. Let's add numbers. Does it have a vector space structure? Quick answer is no. Okay. So it has a group structure, and we already talked about that everything is infinitely differentiable, which means it's a manifold. It's a smooth manifold, which means that in the end, what kind of structure are we talking about? SE3 or SEN? A Lie group. SON itself is also another Lie group. And Rn itself, I can think of as a Lie group. Okay. Rn itself actually has a vector space structure. Usually Rn has everything. Okay. Rn has everything. It has the vector space structure, it has the group structure, it has the manifold structure. And that's why when you're doing linear algebra, nothing is forbidding. Everything is allowed. Okay. So this is the group structure that it has. It will only make sense after you do the homework or the assignment, okay, or both. Okay.
Your order like this.
Yeah.
If this lives in something space and this live in space.
Yeah.
So at the end, the combining set will be also in this space.
Let me rephrase it and hope if you're saying what I mean, that's a very good thing. Okay, so let me rephrase it. If you're saying that this has some structure, so this is a group, for example, and this is another group, and then we take the Cartesian product of them. Does this have the same group structure? Is that what you're saying?
They always live in the same space.
What lives in the same space?
This Lie group and Lie group. So definitely, can we say this?
Okay, that's a good question. Yeah, okay. If this has a structure and this has a structure, does this immediately follow? I have to be careful with that. And yes and no. Okay, and that's actually, you're going to see it immediately right now. For example, when I say that SON has a group structure, what is the group structure of SON? When I give you two rotation matrices, what do you do with them immediately? Multiply together and you get another rotation matrix. So SON has a group structure. You can check it has the identity, it has the inverse, and so on and so forth. Look, so this has a Lie group structure. It has a group structure. What is the group structure of Rn? Addition, exactly. I can add, I can translate by moving forward, or its inverse is backward. And what is the zero? What is the identity? Not translating, staying in where you are. Just like when the rotation matrix, the identity of it is not rotating. This is the identity element. Okay. With the math, it will be clear, all of that. The question is, yes.
So are only closed under multiplication, right?
That's right. Yeah. So they are closed in multiplication, and Rn is closed in addition. There's no such thing as multiplying a vector with a vector. And don't think about, cross product. We haven't talked about it at all. That's something completely different. So taking this one, the question is now, is this the group structure we're talking about here? That if this so this has a group structure, yes. To answer your question, yes, of course. In this simple way, if I take any R from here and I map it with its own group element, and I take any psi here, I map it with its own group element, I've already given this pair a group structure. The question is this the only way I can make a group structure? Let me rephrase that. In this way, are rotations and translations coupled or completely separate from each other? Completely separate from each other, right? Because I'm taking rotation matrices, doing stuff with themselves, doing translation, doing stuff with themselves. Now, this is a question to you. Whoever tried to work with rigid body dynamics or trying to work with robots in 3 dimensions, are rotations and translations coupled or uncoupled? Definitely coupled. Definitely coupled. And this is exactly where your math starts to break down because of this small separation. So yes, of course, you can give it a group structure, but the kind of group structure that SE has is actually this weird one. So what is SE? N, it is the pair. We're going to be calling this pair H. So whenever I say an H, it's already equivalent to the pair of R and psi. And it's the set that have all of the H's such that R is SON and psi is Rn. Make sense? Yeah. Yes. Yeah, can go back.
Let's say we have a 2D plane.
Okay.
Is the end here is 2?
Yes.
But I think the robot can only rotate around the single axis.
That's right. Around the Z. That's right.
So the end here is
SO2. It's SO2. That's right. That's a very good point. I think you're going to have it in the assignment. You're going to play around with this. What you just said, I'm going to quickly say. So in 2 dimensions, SO2 is isomorphic to S1, the circle. And you're going to prove it in the assignment. Okay? Very good observation. But stay with me now, okay? So SEN is the pair of R and psi. We're going to be calling each element of SEN H. What is the group operation from 2 SENs, 2 elements from SEN? So HA and HB. HA has its own RA and psi A, and HB has its own RB and psi B, right? This is how we define the group operation. The R of the B is multiplied by the R of the A. Makes sense, right? Exactly what you mentioned. But the psi that corresponds to the both B and A together is the rotation, is the sum of psi A and psi B, but first we multiply psi A by RB. You see here what immediately that rotations and translation are coupled directly, immediately coupled. There's no such thing as do translations alone, do rotations alone. This is at the modeling level. How about control? What's the first thing you do when you go to control? Control the rotations alone, control the translations alone. If you want to do state estimation, do a Kalman filter for the rotation alone, do a Kalman filter for the translation alone. It all breaks down because of this simple fact. Okay? They are both coupled. Okay? And you're going to see later on, we're going to be continuing in this direction. The question is, why is the group operation like this? You're going to be proving it in the assignment. If it's not clear, if you do the assignment, you can discuss it in person, inshallah. Okay? We haven't, well, I don't know what you're talking about. I don't know what you're talking about. Okay, there's something else. So the way you're going to be proving it, okay, since you asked, is by this. So you're going to be proving it by first taking one Rn to Rn, and then acting with another map on what you get. So here, for example, this is actually the proof. right? Eating 1v, I get this. Eating it again, with another element that corresponds to the phi will give me the equation I just showed you. We're actually going to be working within the assignment. In the same way, you're actually going to be working with the identity element. You're going to be seeing that the identity element is simply the identity rotation matrix and the zero translation vector, but this makes sense already. And the inverse of it is simply the transpose of the rotational part. And for the translational part, we not just do a minus of the translation, we also have the rotation multiplied by it. So if I started like this and I did this transformation, the inverse of it is not simply inverse rotation and inverse translation. It's not the same. I need to do, if I moved like this, rotation and translation together, I need to go rotation and translation together. This is exactly what this statement is capturing.
Was also covered, was not simply a expression.
Absolutely, exactly, absolutely, exactly. Okay. Yes. This one. This one.
Still, we don't know the map where it lives.
Which one? This one? No. This is exactly what it is. It's the map that has that looks like this. That's an affine map. It's not enough to say it's a linear map. So it's not GL of NR. It is actually lives in a slightly bigger space that includes one part of it that's in ON, or property in SON, not in ON, and the other one is in RN normally. And it's exactly in this affine way. It has to be the space of affine maps.
GL and also some other space.
Exactly. So going back to this picture, we had the rotation from this part, and then translation was not here. We're going to be doing a simple trick now, and you're going to see it now. It's not a trick. It actually even has a very deep mathematical meaning. I hope we have time to talk about it. But you're going to see it exactly. Okay, we can. There is a workaround it. Okay.
Something, it will be vector, and this vector at the end it will be vector space. So this translation will be in this area.
No, it will be something else. Don't wait. Okay, nice. Okay, you'll see it. What we have. Okay. So what I just showed you. So this is the group structure of the set SEN. So this is the group structure that we give it. This is the group operation. This is the identity element, and this is the inverse element. Okay. You can check. This is extra stuff that is, you don't even think about. You just, mathematically, you cite or you just mention it in one one line. But you can do it mathematically properly. These are actually smooth maps. Okay? And because they are smooth, they are infinitely differentiable. We can actually say that this is an infinitely dimensional now manifold, and all of these maps are smooth. So this is actually not just a group; it's also a Lie group. Okay, so this is the differentiability structure. What we did now is isomorphic to SON and RN as sets, but not as groups. Okay. So, and this is why you find all over the place that SEN is usually called the semi-direct product of the groups SON with the group multiplication and RN with the plus. And it usually has this symbol. Has anyone seen this symbol before in any paper or anything? You don't read a lot of papers, okay? You'll see it, hopefully. Okay. So this symbol is simply telling you that if I take a pair from SEN, it has a group structure, but beware. It's not simply that R and R are one thing and psi are another thing and they're separate from each other. This simply says that there is some sort of coupling between them. Okay, this is simply what the symbol says, and it's actually called the semi-direct product of the two groups. Okay. Any questions? In what sense? Yeah, you have to always, if the paper is good, it should always describe what notation they are using, and the pronunciation of the.
Should I know, or the paper should tell me?
The paper should tell you up to some extent, because the paper is usually written to researchers, and researchers should have, you know, good foundation. And hopefully this is what we're doing in the course.
Something like this.
That's not usually you mean.
Should I pronounce it?
What do you mean by pronounce it?
What I say, something RN.
Yeah.
What I say, what I pronounce.
Yeah, it's exactly. Yeah, RN and SON is exactly the name for the symbol itself. So this is usually an operator. Okay. This is usually what we call a variable, right? Or a symbol, right? It's an element. And you can mix stuff. The thing is that, you know, this is, you know, in the end, there is some convention. For example, I can call the plus times and you can call the times plus, but we're just going to confuse ourselves, right? Actually, by the way, there are some programming languages that allow you to do that. Are you familiar with that? I think in C you can actually do that. Okay, I think, but if not C, I think there's another language. You can actually define the operator. You can say what is plus. C, right? I think so. Yeah. And other language they tell you no, plus is plus, and times is times, and so on. If you want a new operation, you need to define it, and so on and so forth.
I read it. Should I pronounce it or should I name it for the others? Yeah, and for example, if I want to describe this notation for you or for me,
yeah,
what I should say or read it.
This you have to tell me that. So written like this, you have to say that SEN is defined as the set of all elements H, where each H is the pair of R and psi, defined such that R belongs to SON, where SON is the special orthogonal group, and psi lives in Rn, where Rn is the n-dimensional Euclidean space. That's exactly what I just did. If you write, that's exactly what I just said. Everything here should be familiar from that. Okay. And at some point you go really to like basic stuff. Well, you will not find in the paper that he's telling you that actually the two dots and the equal is as defined that, or this is the notation I'm going to use for sets. There has to be some, you know, we have to have some agreement, right? Or education. That's exactly what we call education. Okay. The symbol itself is not important. Okay. In this context, SON and RN, if you see something like this, for example, A and B, so C is defined as A with this symbol B. It implies that C is defined as the semi-direct product of the group A and B. Semi-direct product. If you see something like this, if I tell you the group is defined like that, it means a completely different thing. This is actually called the direct product group. Look up, okay, two things. The difference between the semi-direct group and the direct group. And this will clarify, I think, a lot of stuff. Okay, yeah, you can do it in ChatGPT, it will give you an immediate answer. This is like basic stuff. Okay. Luckily, so you remember when I told you that the maps, that this SEN, okay, is not a subset of GLNR, right? Because it's an affine map. Remember what GLNR were? Invertible. Nope. Nope. Don't use matrices. Go back. What was exactly the? Nope. Maps. What type of maps? They were invertible. Invertible linear maps. They were invertible linear maps. And affine maps, were they linear? You remember we had in one of the slides, we showed that affine is not an example of a linear map. So the affine map that we use now to describe rigid body motion, rigid body poses, is not a linear map. So we cannot say that it belongs to GLNR. But we can use there are some very heavy, mathematics there. You're always going to see it as a trick. But the whole idea is that this is related to something called projective geometry. Okay? Something very big, it's very deep. But the idea that this group of SEN, which is the pair of R and psi, we can actually embed them in a higher dimensional space. So if I was working with SEN, I can go to a bigger space, which is GLN plus 1. So if this was SE2, this would be GL3. If this would be SE3, this would be GL4. What is GL4? 4-dimension, the space of 4-dimensional what? Invertible linear maps. But not all invertible linear maps of 4-dimension would work. I need to restrict them a little bit to stuff that look like this. All the stuff on the bottom row, they must have zeros and one. This is a 3x3 matrix. So assume that this is in 3-dimension. Okay, so this is SE3. So this means that R is in SO3. It's a 3x3 matrix. It's a 3x3 rotation matrix. So this is a 3x1 vector. So this is a 1x1 vector, and this is a 0. This is a 1x3 vector. 1x3. So there's just a matrix of zeros, 3 zeros next to each other. And this is what we're going to be calling capital H. The capital H, which lives in this space, and it's a subset of the general linear group in 4 dimensions, if you're talking about SE3, is actually called the homogeneous representation of this element. Okay? And this is usually what you start with in robotics. Okay? You see how much math is there? That's all. Why is this idea of going one higher space, is it nice and so on? Why is it? Simply because if you take two homogeneous matrices and you multiply them together with the normal matrix multiplication you're used to, see what do you get there? You get the group operation that corresponds to SE3. See? And if I take the inverse of the matrix, inverse of a 4x4 matrix is a nightmare. But in this special case, because this is not just any general linear map, so it's this special homogeneous matrices. You get this very nice structure that you can simply just calculate by hand. I don't need to do any determinants or divide by stuff and all of this abracadabra that you do for inverses. Just very simple that the rotational part is the translation, is the transpose of the other one, and the translational part of this homogeneous matrix is the transpose of the matrix of the rotation multiplied by the psi with a minus sign. But there's something that's missing, which is, you remember when we said that this R and this psi, they were acting on some vector. So they were acting on Rn, right? Because R and psi, we defined them as a map, right? Which is what we called here by the phi. So phi was a map from Rn to Rn that must have this expression. So there are two ways of looking at it. There is the matrix itself, which is the M. So there is the numbers themselves, which is the M and the psi, or the R and the psi, the rotation matrix and the psi. And there's the map, which is, as a map, it eats a vector and gives you something else. This is the map itself. So how can we, using this higher dimensional matrix, capture this action acting on Rn? Simply because now we have an action, we had earlier an action of SEN or Rn. We're going to be now identify an action of homogeneous matrices on Rn plus 1. What do you put down there? Just 1. So every vector that we have, we just added 1 dimension, we just add a 1. And then if this was a small v, we're just going to call this a capital V. And this, if you multiply these two together, you see we still have the 1, it doesn't change. And on top, we got the action of the map that we had. V, so the capital V, which is simply just the original vector that we started with, and you just add the 1 there, you call the homogeneous coordinates of V. Homogeneous matrix, homogeneous coordinates, and all of this idea of going 1 dimension higher is a branch of mathematics called projective geometry. It's a branch of geometry there, and it has some physical stuff related to it. So that's the last slide, and that's the summary of everything we discussed. Usually you start here in robotics, okay? But there's a lot of stuff that you need to make clear. First is that just looking at robots, okay, in an environment, we need to make sure that everything should be well defined without any numbers. So this is the abstract configuration. You need to understand that what is the abstract configuration of a rigid body, and what's the idea of a relative pose between one body and the other, okay? Without any numbers. You only go to numbers after you choose the basis, which is one frame, one coordinate frame attached to every observer, every Euclidean space that you have. And in the end, this will give us, between any two frames, it will give us a rotational matrix and a translation vector. Okay? They both together live in what is called SEN. SEN is a group. It's a Lie group. It has a group operation defined as just by what we call the semi-direct product of SON and Rn. And in the end, we can still do everything in normal matrices that you love by just going one dimension higher and going to an embedding to this higher dimensional space, which is what we call the homogeneous, okay, transformation matrices, which is a subset of the general linear group, but in n+1. So what is the correct space that corresponds to higher dimension? So the corresponds to rigid body motions in n dimensions. It is the general linear. It's this one, which is a subset of the general linear group in n+1. And that's it. Any questions? So I think there was someone had this. Yes. So there are two ways of looking at it, either as a trick or with the math. So with the math, it will take us some. So you have to spend your time, wisely. Okay. So we don't have infinite amount of time. Unfortunately, I wish I could. We can go through it, but you need to do it on your own. This is related to the projective geometry stuff. But here, simply as a trick, is that we want. You remember what we said here, that on the top, the rotational part and the translational part, they correspond to the same action of the map, and the inverse element of the inverse action of the map on Rn, this is the rotational part and this is the translational part. And you see, we just get them by this higher dimension. Naturally, if you want to get this, okay, operation and not change the bottom one, because if this changes, oops, sorry. So if you see here, we started by some vector on 1, and we ended by another vector on 1. So we started from a map from Rn, and we ended in Rn. Even though we had the ones there, but the ones were only just as a placeholder, just to act, just to incorporate the translational part. See, that's actually the idea. So the affine map, okay, in Rn, in n dimension, when we went to one dimensional higher, became actually a linear map. That's the whole trick. So the affine map in n dimensions is not linear, but it's linear in a higher dimensional space. This is the whole idea of the projective geometry. No, any, don't go any. I will not know. Okay. It's not actually all of the general linear map. It has to be a subset of it that have this structure. The general linear map in n+1 dimensions, if let's say, for example, n is equal to 3. So general linear maps of four dimension. What are they? They are n by n matrices that are invertible, determinant not equal to 0. But this is a very special case of them, right? So here I can have anything and any numbers in the last row, right? But here no. We said we have to have zeros and 1. This is the idea of the projective geometry, and this is why it's a subset of the general linear group. Any more questions? Let's see how much time we have. Still have a couple of minutes for questions. Yes.
Same restrictions on the like the translation and translation and rotation and
reflection. Yeah. Nothing changes. Actually, first of all, we excluded the reflections by looking at only at the determinant equal to 1, okay? And we have the translations anyhow. Okay? That's it. So both were there. The fact that the only problem is that written like that, if we have these two, and we're thinking of actions on Rn from Rn to Rn, it's not a linear map. So it did not belong to GLN R, because it's not a linear, because of the translation, exactly. So what was the trick or this idea of projective geometry? Go one dimension higher, the affine map will become linear in this higher dimension. And this is why we were still working in 3 dimensions. Everything is 3 dimensions, but we're going to be working with 4x4 matrices. Just because of this fact, we want to have translations and rotations done by group matrix multiplication. Yes.
How can it be invertible? No.
This one.
No, this one. Yes.
This one.
Yes, this one.
Yeah.
First equation MB plus psi. How can it be invertible?
That's the Haas limit. So you're going to be what?
Because of the tolerance.
We're gonna Have the assignment, don't worry. So you're going to be showing in the assignment. This is actually your starting point in the assignment. If you want to prove that, where does this come from? Take the map, this one, and act on it twice. So act once, get one vector, and then act on this one vector again. But in the first time you call, for example, H1, and H1 has M1 and Psi1, and the second one you have H2, and H2 has M2 and Psi2. Of course, the M here will be R, okay? Because this is still the M and ON. And if you want to do the inverse, well, how was the inverse defined? Does anyone remember? Exactly. It was the element, okay, that when you act with you take the group operation with this element, which is H inverse, and the H, you get the identity. If you know what the identity looks like, you can, and you know what the H looks like, you can already solve for how should the H inverse looks like. This is exactly the second part. This is what I'm saying now is the assignment, what you should be doing in the assignment. Okay. You're also going to have some in the assignment, some numerics and some MATLAB code where you're going to be playing around with this idea of maps, and you're going to be seeing if I have a map here or here or here or here, what does it do? We're not going to be looking at that one. Okay, we're going to be looking only at endomorphisms. So I'll give you an example of this map, and I'll tell you calculate what does it do for the vectors. And you're actually going to be drawing it, and you're going to be doing it in a MATLAB code so that you can see it for num. So you're going to be drawing it for two vectors so that it's easy to calculate on paper. You're also going to be writing some MATLAB code, or ChatGPT will do it for you. Okay, and you're going to be seeing the visualization yourself from an element from here, an element from here, an element from here. You're going to be seeing really that actually we're going to be this action from this a map that looks like this will do rotation, this one will do translation, this one will do something that's not translation or rotation or reflection, and so on and so on. So that's for the assignment, inshallah. More questions? Okay. Sorry? Okay, on that point, okay, so let me stop the recording so we can